All right, the next chapter is about the crude oil. Since most of the organic compounds are coming from the same source, which is crude oil, so we are going to learn about this industry and what is crude oil and how do we take our products out of it. So to begin with, the crude oil. What is crude oil? Let's start with its origin. Millions of years ago, plants and animals living in the sea died and fell to the bottom of the ocean. Layers of sediment, soil, cells, sand formed on top of them. Their shells and skeletons form limestone. The soft tissue was gradually changed by heat and high pressure into crude oil. Crude oil is a finite resource, non-renewable resource, which means this resource, if we keep on using in the same way, is going to end one day. And we are predicting continuously about petrol on the top of the list that we might finish all of the petrol from the Earth's crust by 2050 or earlier, which means it's a non-renewable resource, which means there is a finite amount and the supplies will not be replaced for many millions of years to come. That's why we're coming up with alternate energy sources. But that's not the point for today. Continuing with crude oil, what crude oil is made up of. So crude oil is actually a mixture of hydrocarbons, the compounds containing carbon and hydrogen only. There are lots of different hydrocarbons in various sizes in crude oil, ranging from molecules with few carbon and hydrogen atoms, like just two high carbon atoms, or just three carbon atoms, or just four carbon atoms, to very big molecules containing more than 100 carbon atoms in a single chain. So all of the kinds are present in the crude oil. So how are the physical properties of hydrocarbons changed with the molecule size? We need to understand this since this is going to help us with the understanding of crude oil as a whole. So let's continue with it. As the number of carbon atoms in a hydrocarbon molecule increases, the physical properties of the compound change. Most of these changes are the result of increasing interactions between neighboring molecules. How is that so? Molecules become bigger and there are more points of attraction between them. So attraction becomes stronger. For example, I'm going to give you an example of methane. One methane molecule is going to attract the other methane molecule with just one simple attraction point. But if you're talking about a chain of butane, let's say there is a chain of butane like this, and then there is another chain of butane like the similar one above, and when they are going to go for attractive properties, let me tell you, this one is going to attract over here, this one over here, this one over here, this one over here. So you'd notice that as the chain length increases, the number of attraction points increase. When the number of attraction points increase, actually the intermolecular forces of attraction become stronger. And when they become stronger, it's more difficult to pull one molecule away from its neighbors. So when molecules become bigger, the following list of changes occur. Let's go through all the list of changes one by one. Number one, boiling point increases. The larger the molecule, higher the boiling point. Why? Because larger molecules are attracted to each other strongly than the smaller ones. So this definition, this drawing is going to help you a lot. You can see that the larger molecules, and even this is not a larger molecule, it's just an example in comparison. Don't forget, we have molecules that have over than 100 carbon atoms at a time. So, of course, there are going to be hundreds of attraction points between one another. Of course, the energy, the amount of energy required to break these strong intermolecular forces of attraction is going to be pretty huge. So that's why the boiling point increases for larger molecules. Now, the liquids become less volatile as they become larger molecules. The bigger the hydrocarbon, the slowly it evaporates at room temperature. Again, due to the attractive forces, the reason is going to be the same as shown in this diagram. It's just that different properties are changed differently due to the exact same reason, intermolecular forces of attraction. So the liquids become less volatile since the vapors do not leave each other easily at room temperature, so it slowly evaporates, and that's solely due to the field structure or the forces of attraction among them. So the liquids not turn into gases so easily. Although shorter molecules may still do the same and be very volatile, but the larger molecules aren't. When we talk about the larger molecules, and specifically the liquids become more viscous, which means they flow less easily. They contain bigger molecules. Since smaller molecules are runny, the bigger molecules flow less easily because of stronger forces of attraction. Now, if this molecule would like to flow, it must be getting attracted to the other molecules surrounding it, and the flow becomes difficult. Hence, the term more viscous. Viscous means resistance to its own flow. So, the attractive forces are actually a resistance to its own flow. Moving on, the liquids become darker in color. Closer are the molecules to one another, darker the appearance. Farther are the molecules from one another, lighter the appearance. That's one of the easiest rules. Moving on, hydrocarbons do not burn as easily as the smaller ones. Smaller ones burn easily, produce a large amount of energy. Of course, the bigger ones are even going to produce huge amount of energy, but they cannot be lighted or they cannot be burned that easily. So this limits the bigger molecules to be used as fuel. We can't actually directly use them as fuel. And I hope if I talk about your daily life, this can be taken from daily life observation. Now, the gas that you commonly use for cooking or the liquid that you commonly use for different purposes like a car fuel or as such can be easily burned. They actually catch fire really quickly. But if you take a look at the coal pieces that we commonly use for barbecue purposes or bonfires, it's difficult to light up the coal. So the solids, the ones that have bigger chains, are difficult to light up as compared to their liquid or gaseous counterparts, which have smaller hydrocarbon chains. So that's what we are talking about in this point. Let's clear it all up. Let's move on. Okay. So, how do we separate crude oil into different substances according to our own advantage? So, crude oil itself has no uses. It has to be separated into fractions or parts before it can be used. These fractions are all mixtures, but each one contains a narrow range of sizes of hydrocarbons with similar boiling points. We use fractional distillation to separate crude oils into fractions, hence the name fraction. Fraction itself means parts, the distillation that is carried out in parts or that give away their products in different parts. Since the products have similar boiling points are actually mixtures as given in the lines above. So now we carry it out in oil refinery. Let's discuss the fractional distillation that we carry out in the oil refinery. Crude oil is first of all heated. Now, this is the heater. I'm going to go line by line from here, and I'm going to at the same time explain on the diagram what's happening. So we're actually starting from the bottom of the fractional distillation column, and there is a heater at the bottom which boils everything, and then the vapors are passed into the fractionating column. Now, at the bottom of the fractionating column, the temperature is the highest due to the presence of heater right next to it. As soon as the vapors rise up, since they go farther from the heater, they start losing their heat and they become cooler and cooler. So much so you notice a difference from 400 all the way to 40 degree from the bottom of the fractionating column all the way to the top of the fractionating column. Now, how far up a particular hydrocarbon is going to move actually depends upon its boiling point. Suppose a hydrocarbon boils at 120. At the bottom of the column, the temperature is much higher than 120. Of course, that's around 400 degrees centigrade. So it's going to rise up. Anywhere near to 120, it's going to get separated. All right. As it travels up the column, it stays the gas around the temperatures higher than 120. When the temperature falls to 120, the hydrocarbon will turn into a liquid, it would condense, and it can be removed. Since the stuff can be removed at one point, you'd notice we're removing bitumen at the bottom, fuel oil over here, diesel over here, kerosene over here, which means they have lower boiling points as we go higher, gasoline over here, which we also call petrol, and refinery gases over here, which gives us the idea that these have the lowest boiling point, of course, and these have the highest boiling point. So the fractionating column is actually separating all the fractions or the hydrocarbons on the basis of their boiling point. Higher the boiling point, more bottom position it is going to cover at the fractionating column. Lower the boiling point, the higher it is going to rise up in the fractionating column and will turn out at higher checkpoints. The same thing is written in the paragraph. Smaller molecules have lower boiling points, they get further up the column before they condense, and the longer chain hydrocarbons have higher boiling points, they condense lower down in the column. This way, the crude oil is split into various fractions apart. The boiling point is same as the temperature at which the gas condenses to form a liquid. It can also be known as condensation point. So whether they use the word boiling point or condensation point, it pretty much means the same thing over here, since we are actually manipulating the same piece of information into a different process this time. All right. Now you will find a lot of disagreement from various sources about exactly what fractions are produced in the fractional distillation. Figure 23.3 matches the requirements of Edexcel IGCSE specification, but this is a major simplification of what is really going on. Since the process, what is really going on, is pretty complicated, so we have simplified it for your ease. So 1, 2, 3, 4, 5, and 6 fractions, and that's about it. That's how easy as it gets. All right. So let's move on. Let's see what we have up next. The hydrocarbons in the refinery gas fraction have very small masses since they actually go highest up the column. Their boiling points are so low that the temperature of the column never falls low enough for them to condense to liquid. The temperature of the column isn't hot enough to boil some of the very large hydrocarbons, so they remain as liquid and they stick to the bottom. We call them bitumen. They are removed as the residue from the bottom, since the temperature of the heater doesn't affect them much. So bitumen is like the residue, since no change happens to them, and refinery gases go to the top. Refinery gases go to the top since they stick as gases. Moving on, uses of these fractions. Now, each of these fractions have their own independent set of uses, but there are some common generic uses as well. To begin with, the most important of all uses, as fuel. Most of the hydrocarbons are used as fuels. They burn in air, excess of oxygen, they form carbon dioxide and water, like we just studied, and they release a lot of heat in the process. These fractions can therefore be used as fuels. A fuel is a substance which, when burned in oxygen, releases heat energy. And this heat energy is then converted into various forms of energy and is commonly used. For example, burning of methane. Methane, being one of the simplest hydrocarbons, the smallest one as well, is the major constituent of natural gas. We're using methane around the world for running our cars, for cooking of food, for heating up our homes, or in the industry for different industrial purposes. Octane, one of the hydrocarbons present as a major part of gasoline or petrol, C8H18, again, one of the most common car fuels used around the planet. But you'd see that both of them react with excess amount of oxygen, giving the product carbon dioxide and water, the equations like the ones you've just tried to balance. But I told you at that point that we have two different types of combustion. For these equations, you would see that this is complete combustion. What is complete combustion? When you have excess of oxygen. When your products are specifically carbon dioxide and water. So what's the other type? It's actually the exact opposite, incomplete combustion. What's that? When there's not enough air or not enough amount of oxygen. If there is not enough amount of oxygen, what happens is that this leads to the formation of carbon soot or carbon monoxide instead of carbon dioxide. For example, if methane burns in badly maintained gas appliance or in a closed room or in a poorly ventilated area, there won't be enough oxygen to produce carbon dioxide. So you're going to get toxic carbon monoxide instead. This is carbon monoxide. As much as carbon dioxide is not harmful at all, carbon monoxide is toxic. It can give you anywhere from a headache to dizziness to nausea, all the way to turning you unconscious, or even capable of killing human beings if breathed in for a longer duration of time. Right? Let's discuss about it more. Formation of carbon monoxide from incomplete combustion is very dangerous. It's colorless, it's odorless, and it's very poisonous. It is poisonous because it reduces the ability of our blood to carry further oxygen around the body, since it bonds with the protein that is capable of carrying oxygen around the body. What happens? This will make you ill. It usually starts with a headache. The headaches turn to nausea. The nausea turns to dizziness. The
Yeah.
dizziness turns to unconsciousness. And finally, if for like a period of 30 to 40 minutes you stay in the same environment, you might die. Not getting enough oxygen gets the cells in your body to respire respiration to provide more energy. And when they're not going to get energy or they're not going to get oxygen for respiration, the cells will starting to die. So your organs starting to fail. This is one of the most common sources of death around the world, where the combustion is carried out in poorly ventilated areas. So, whenever you're going to carry out combustion, make sure you have well ventilated areas. And this is going to work as a precaution in your lab work. Don't forget, every lab work that has burning or a flame involved, every time you're going to see or go through the same precaution that there should be proper ventilation. Carbon monoxide actually combines with hemoglobin, the protein that carries oxygen in the red blood cells around your body, prevents it from carrying the oxygen. It actually binds more strongly to hemoglobin than oxygen does. All right. So refinery gases. Refinery gases are actually a mixture of methane, ethane, propane, and butane. These are all gases. We can separate the individual gases if required, and this is commonly used as liquefied petroleum gas (LPG) for domestic heating and cooking. Let me tell you, your country, Qatar, is one of the most LPG producing countries around the world, and that of the highest quality too. Moving on, gasoline or petrol, among other fractions, it's a mixture of hydrocarbons with similar boiling points. Main use, car fuel. Kerosene is next on the list. It is actually a fuel for jet aircraft. It is also used as domestic heating oil and paraffin for small heaters and lamps, which is actually an obsolete use for the developed countries around the world. But for somewhere like Africa or India, this is still used for the same purpose. However, jet fuel is one of the most common uses. This goes for military planes as well as domestic planes. Next up is diesel. Diesel is actually a fuel for heavier engines, buses, lorries, some heavier, bigger cars, railway engines, and this can also be converted into more useful organic chemicals. This process is known as cracking. We're going to go with this process in the later part of the chapter. Next up, fuel oil. This fuel oil is in some books also mentioned as ship oil. since the name suggests, it's the most common fuel for ships. Last one on the list is bitumen. Bitumen is a thick black material. It is melted and mixed with small pieces of rock to make the top surface of road, and during that time, you're gonna find it really sticky. That's how we are able to make good roads. So this actually completes the whole set of points. Just give me a quick second.